So the chapter that we study now, I don't know how it is named in the new book, but this chapter is all about laws of motion. And this is how we read it in physics. Laws of motion. Okay. Laws of motion. Somebody will read it as exploring forces. So this chapter will be hovering all around. This chapter falls under kinetics. Kinetics, where we will try to answer, we will be studying motion itself. We will study motion, and our motion will be again uniformly accelerated motion in a straight line, because we are kiddos of grade 9. We won't have complicated motion. So we will have this, but here we will be learning the aspect why. Why does this motion happen? In the previous chapter, you learned about facets of this motion. Like this motion has a displacement, this motion takes time, it has a final velocity, accelerated, non-accelerated, retarded, decelerated. Today our question will be why. Hota to kyun hai, theek hai? And this chapter will introduce you to something which we call as classical physics. Classical physics is study of everything before atomic physics came into picture. So we will be going to the era of 1600s, 1700s, which is also known as Newtonian motions and all. So classical physics, in classical physics, this chapter is about classical mechanics. Okay, mechanics. Here you won't learn about how an electron moves, but you will be learning about very nice things. There is a rope out here, and there is a monkey out here who is holding the rope, and this is the tail of the monkey. What is the tension being created out here? Right? Everything is seen as objects. Your study is like a billiard table, where every billiard ball will be there. You know their mass, you know with what force you are hitting, you know what is the velocity, how much friction. So you can predict everything. That is called classical physics. Classical physics views the universe with a deterministic model. It's like a clockwork. The clock has a gear which moves this much, this much, this much. So if you know how much it is moving, you can say 30 days from now, where will be the position of this handle? You can calculate. This is called classical physics. Everything we know, we can predict. And if you are wrong in your prediction, classical physics says either you were an idiot to measure it, or you did not have the proper measuring device. But we have another branch of physics which is called quantum physics. In quantum physics, the uncertainty is built into the system itself. It is not that you are not being able to measure. Today, if I don't stitch a shirt properly, what do we say? Either you didn't know how to cut it, or you didn't know the proper measurement, or you didn't have a tape. Otherwise, you should have stitched the proper shirt. Classical physics says like that. Quantum physics says no matter how much you stitch it, there is a bit of uncertainty in this whole universe, which you cannot predict. And only so those discussions are there, but our study will be all around classical mechanics. We'll see big objects out here, right? And we will be talking about the main item that we will be talking in this chapter would be about force, and you will get into depth of it, right? So chaliye, let's, and first part is all grade 8 part. Okay, let's talk about force. Let's talk about force. So force, what happens? A force is an influence which acts on a body. Force is an influence, right? Like in plain language, how do we define? We say the push or pull. The push or pull that happens on acts on a body is called the force. So in better sense, we say it's an influence on a body, and it happens due to interaction of two bodies. There has to be. Force is an outcome. Okay, it's an outcome of an interaction between two bodies. This is what is the difference I'm saying. When your generation comes in my age, now you all be able to write like this. We are able to write. Our teachers taught us. Practice. Okay, is an interaction, is an outcome of an interaction between two bodies. Now, whenever there will be two bodies, there will be an interaction between them. Okay, so say suppose this is, say, my body 1. This is a person, right? And this person is trying to put a force on this body. He's trying to say push this, right? So two bodies will be involved, and this is the interaction which is happening. The force is an outcome of an interaction between two bodies, and this outcome, you will see is acting either as a push or a pull on one of the body. On one of the body. Right. These bodies are further can be classified as, one can be the applicant of force, okay, one who is applying the force, and one can be the recipient of force. Clear? Like here, the person is the applicant who is exerting the force, and the body is, this is the recipient. So on whom we will see the effect? We will see the effect on the recipient. If you are seeing the effect from this side, it is like a push, and if you are seeing the effect on this side, it is like a pull, right? So push and pull are two perspectives, same thing seen from two different perspectives. I think this much is clear, okay? So little bit of revision as we go further. Then in grade 8, we also studied that forces can be two types. We say contact forces or non-contact forces. Non-contact forces. When we talk about contact forces, the muscular force was studied by us. The force exerted by our muscle. This is a classic example of muscular force, right? Friction is a type of a contact force. Remember, the force which opposes the direction of motion created by force is called friction, okay? And in non-contact, we studied three forces: gravitational, there should not be any contact between the two bodies. Then electrostatic, and then we studied one more, which was magnetic. Here, the two bodies need not be in contact with each other. While gravitational is always an attractive force, these two forces can be attractive as well as repulsive also. They can be repulsive also. Electrostatic force, the force created by two charged objects, force experience created by two charged objects. Gravitational, the force exerted by a body on any other body. And this chapter is anyway taken out, otherwise it was our third chapter, which was a very interesting one. Magnetic force, force created by two magnetic bodies, okay? Itna clear hai? Right? Again, grade 8 topics only. Fine. Further. Can I change? Yeah. This is, I'm just trying to make a mind map, pulling you through what you had studied in your previous classes. So we'll just try to revise those. Fine. Can I go ahead? Okay. Then we also studied something called characteristics of force. Characteristics of force. So what were the characteristics of force? Number one, if you apply a force to a moving body, then what all you can do? You can, now we are in higher classes, so I won't write so many points. So let's say we can change its velocity. Means you can either increase its velocity or you can decrease its velocity. How you can decrease? By applying an opposite force. Cyclist is coming towards me, I have applied a force. So the cyclist velocity can reduce. Second I can do is that I can change its direction. A bowler is bowling at a very high speed to me. I just open the face of the bat and just run it down to the third man. That is what? Change the direction of a moving body. Which one? Change in direction, change in velocity. Yes, you can say that. Change in velocity, maybe that to speed also. Sometimes we can change the direction of a body. You are correct. It can come there. Then I can also bring it to rest. Right? The same force, when applied to a body at rest, then what all I can do? I can bring it to motion. And another thing I can do is, I can also change its shape. Take a atta dough, and the atta dough is in rest, apply force on it, you can change the shape of the atta dough. These all are grade 8 topics, right? And you can give examples of each of them. A stationary football, you just kick the football, stationary body to rest. A moving body can be brought to rest. Clear? A body which is moving, you can change its speed. You can also change its direction. I think Ryan has a point. So why not I make this word as speed? Makes it better. What happened? Yeah. Speed. And if I combine these two, it's actually velocity. Nice observation. Thank you. Okay. This is all we had studied. Okay. Few more things we had studied in grade 8, though we did not know anything about it. We studied what was the SI unit of force. The SI unit of force is Newton, which is written in capital N, but when you write the value of the force, it is actually to be written in small letter, newtons. So Newton. Newton in capital is the name of the person. The unit is always in small letter. However, when we write 5 Newton, you can write 5 small newtons or write 5 capital N. Okay? This is the SI unit. If you want to know the CGS unit, the CGS unit is dyne. Dyne. We'll see all what is the combination between each. CGS unit is called dyne. Okay? No, don't write dyne, dyne. Right? So let's go to anything that you want me to go in depth in this grade 8. These are again, I mean, the new science book of grade 8, which is curiosity, and your science book exploration. This part is common actually. This is the same thing. All right. So if you want that anything you have not understood here, do not hesitate. I think you have so far. हाँ बोलो. Newton. Newton ऐसा है. When you write a force of, you can write like this, a force of 5 newtons, right? Mathematically, when we do, we write it as 5 Newton. You should not write 5 newtons N capital. 5 newtons is this or this. Newton is the name of the person, Isaac Newton, after whom this has been done. So Newton is the SI unit of force. Even if you see MKS units, though like you should know all these. MKS, like when we did our engineering, we used to study MKS unit also. The MKS unit of force is kg force, where F is written in bracket. Kg force. Kg force. Then only you will understand what is the difference of mass and weight. This is kg force. Right? That's the reason that when you read pressure, pressure is what? Force upon area. So you will be reading it as Newton per meter square, which is also known as Pascal, bhul gaye, which is PA. In our days, we used to read it as kgf per cm square. You'll read this also as unit of pressure. Force. And when you go to fill your car tires, then you follow the FPS system. So in FPS system, force will be written as LB inch square. And this is known as PSI, pound per square inch. You can write in FPS, the foot pound system, it is known as LBS, means pound. Pounds is LB. When you go to petrol station, the air is always filled in FPS. So 36 karte hai na, that is PSI. Try to open the driver's door of the car and see a sticker where actually the door's hinge goes and fits. Not the door's hinge, the door lock. You open the door, then leave the door. Look in this part of the body of the car. There will be a small brass rectangle. There will be a sticker. How much inflation you should do. They will write everything. They will write in Pascal. They will write in kgf per cm square. They will write in bar. These are all units of pressure. Then they will write in PSI. The fuel station gauge can be converted to kgf per cm square also. But the whole fuel station will laugh at you saying that you don't know. Actually, you know better than them. Because we are gulams of Angrez, so we are habituated to using pound per square inch. Cake still is measured in pound. because you are a British slave. Otherwise, cake should have been measured in, weight is to be measured in Newton. Okay. चलिए इतना समझ में आ गया? आगे. Right. Now we come to our concept of balanced versus unbalanced force. Balanced versus unbalanced forces. Before we go into balanced versus unbalanced force, so there is one more topic which I wanted to cover. Now, since it is a quantity, force is a vector quantity. Is a vector quantity, and the best way we represent force always is with an arrow. It is the easiest vector to understand because you feel that there is a direction and you feel that there is a point of application of force also. Understood? So this is a vector quantity, means this quantity will have both, it has a mag plus direction. Mag plus direction. Though in grade 8 you will be dealing more with only the mag part, the magnitude part. So we come to balanced and unbalanced forces. Okay. So let's see the concept of balanced and unbalanced, and we also see how does this affect what is known as equilibrium of a body. So let's have, this is a body, right? And let this body be under the influence of forces. Okay. Let's say I'm having one force out here, right? And I have another force. Now this will be useful for your grade 11s and all. Say this is another force, and I arbitrarily say that this force is 5 Newton and this force is 7 Newton. Have you understood? This force is 5 Newton, this force is 7 Newton. So first we say, what is the net force that is acting on the body? What is the net force that is acting on the body? The net force is, we add forces which are in the same direction. Algebraic addition. 7 Newton plus 5 Newton is how much? 12 Newton. All right. So 12 Newton force is acting on this body. You can show as a 12 Newton force as a push or a 12 Newton force as a pull, because this arrow which you have drawn is a vector, and a vector can be translated parallelly, as I told you. इसको कहीं भी लेके जा सकते हैं. See, what becomes arbitrary out here is that somebody might ask you, what is the net force acting on the body? So if you are at a lower level, let's say grades, when we are studying physics at elementary level, person will do what? He will add up both and say in a magnitude, we will put an arrow which is exactly, say, the sum of the two in the scale factor terms, right? And I start writing here that this should be the 5 Newton force which was already there, the 7 Newton force which is there, which is equal to 12 Newton. I'm correct. What goes wrong out here is that, since you're in grade 9, you should also understand this part. This is something which is known as the point of application. Point of application. Now, what is the concept of this point of application? Sir, you said that vectors can be parallelly translated. You are applying a force on my ear. You can parallelly translate it, brought to my chest also. Do you think the impact will be same on me as a body? No, it won't be. Then why is this translation allowed? Why do we allow this translation? Because whenever we do all this study, like we study for a car, or we study a body, or we study a block of wood or whatever, our study conceptualizes everything into something which is known as point object. Point object. End of the day, the study brings everything into a point object concept. The whole object is brought like a point. Now it doesn't matter how you bring the force. You can slide the force. Do you understand it? But here, it is not exactly that it is the net force acting on the body is 12 Newton, but you can't specify 12 is acting here. Imagine if this was an atta dough, don't you think the piercing would have been more out here? The piercing would have been less out here. So this is a factor we have to address. But if this was something which is like a very small, I bring it into a point concept. I make the atta ball like a bundi raita's bundi. At that time, the 12 Newton force justifies what I have tried to say. So in this grade, we will also concentrate on something based on this discussion, is these lines, okay? These lines, and these are very important for us to understand two perspectives. Sorry. We will understand these lines, and this is my line of action. Line of action. On which line is the force actually acting? Means if the force was like an arrow which has been shot into, hot arrow shot into a block of butter, then how will the arrow come out? I don't expect the arrow to come out of here. This is the line of action, this is line of action, right? So let us first see the problems from kiddo perspective. As a kiddo perspective, what is the net force? 12 Newton, right? Then say suppose I have another scenario where this is 12 Newton and I apply two forces which are say 6 newtons each. 6 Newton, 6 Newton, right? Now total force on this side is how much? 12 Newton. Total force on this side, 12 Newton. So what is the net force? The net force is 0. In this case, net force is 0. Net force is equal to 0. Net force equal to 0 does not mean that body will be in equilibrium. Body may not be in equilibrium also. Those are things which we will try to see, right? This is one scenario. And say, if I would have said that this is 10 Newton, this is 16 Newton, then what is the net force? We have got 10 and say 6, which is 16 Newton on this side, 12 Newton on this side. The whole diagram can be replaced and drawn with one diagram, which is showing one force of 4 Newton from this side. Did you understand what I'm trying to say? I'm saying, imagine a scenario like this, beta. This, okay, let me clone this. Clone. Should it come out? Yes. I'm saying, right. I'm saying this is 6 Newton and this is 10 Newton. This whole diagram can actually be represented by only, by only one diagram, which is 4 Newton on this side. Did you understand? You could have also put a 4 Newton pull here also. That is also correct. Nothing wrong. Means what I'm trying to say is that the whole diagram could have been also replaced with just a 4 Newton on this side. This is also correct. Nothing wrong. These all you will be doing a lot when you will be studying something called free body diagrams in grade 11. Free body diagram means you make the body free from all constraint and try to show what all forces are acting on the body. That's called a free body diagram. Isolate the body. And like say suppose there is a stair, ladder, and on that ladder I am standing. Now you want to find out what is the net force acting on that ladder's footrest, that particular foot level or footrest level. So it's not only my weight, there's a reaction, there are forces which are reaction forces coming from the side. So you will separate the ladder and you'll finally draw all forces. That's called a free body diagram. And then you'll see how many forces can be cancelled from each other, so that end of the day we have to bring it into one body, one force system. Then only all mathematics happens. One body, one force. Like you brought this into one body. But these are very easy scenarios. Okay? Understood this? Okay. Now let us see something more interesting. Okay. Let's see something more interesting. So get the idea of balance forces. Forces are said to be, forces acting on a body are said to be balanced if the net force is equal to 0. Understood? Net force equal to 0, I will call it as what? Balanced forces. And if the net force is not equal to 0, I will call it unbalanced. So let's see one more interesting observation. Let's say this is something that you have already studied in grade 8. So let's see this. A piece of block is resting on a horizontal surface. A piece of block is resting on a horizontal surface. What you are trying to do is that you are trying to pull this block. You are trying to pull this block. And while you are trying to pull this block, you are trying to pull it with a force, say F. You are applying F force to pull this particular block. Clear? Understood this much? Now, as soon as you start pulling it, since this block is actually lying on this particular surface, it will encounter friction. And friction force always acts on the line joining the two surfaces. A frictional force F will be created. Friction always opposes the force which tries to move it. But friction is a limiting force, right? So when you are applying your force, let's say friction, remember, friction is like your conscience. If you try to steal something, it will tell you, don't steal. Still you steal it. Next day when you steal the same thing, it will not say anything. You want to steal something bigger, it will again tell you. So it's just a limiting force. It's like limit hai. So this is a limiting force. Limiting force. And there is no way we can calculate friction. We can calculate friction only by the reverse analogy. What is the reverse analogy? Suppose this person is pulling this up, and this process is say this process is automated and measured. What do you mean by automated and measured? It is not that you are pulling it, slowly the force is increasing, right? And then you find that on a scale, say 0 to 0.2 Newton up to 0.2 Newton, this block was not moving. When we started increasing it more than 0.2, the block just started to move. The block just started to move. So we would say, how much is the force of friction? 0.2. Friction को हम कभी direct measure नहीं कर सकते. We can't measure friction directly. Friction is always measured indirectly. But 0.2 is the maximum friction that you will get here. Now in this case, say suppose this boy is pulling this with a force, and I have quantified this. This is equal to 0.2 Newton, right? At this moment, this boy is pulling it with a force of say 4 Newton, right? Then we will say, what is the net force? This is very important topic in your grade 9, net force. End of the day, you have 50 rupees as your pocket money. Your grandfather came with love, gave you another 20 rupees, but you ate 40 rupees worth chole bhature. End of the day, don't say that you are 70 rupees rich. 70 minus 40, your net revenue or net purchasing power is how much? 30 rupees only. Do you understand? So the net force in this case would be whatever force you have applied, and if you are taking it as positive, means in this direction, force is a vector. If you are taking this direction as positive, then obviously this direction will be negative, and that's the trend. The right hand side is always taken as positive. So 4 Newton plus minus of 0.2 Newton, which I'll say is 3.8 Newton, is the net force that is acting. ये net force को बड़ा समझिए इस chapter में. Net force will be haunting you like anything in this chapter. Net force. It is not important what are the forces acting on a body. Yes, it is important for me to understand the dynamics of the force acting on a body. End of the day, all these dynamics have to be brought down to a simple story. What is the net force? Means finally, I can say one thing. If the block is in motion, then one thing is for certain, that the block is experiencing a net force, and this net force is how much beta? This is 3.8 Newton, and in this case there will be a motion in this block. इतना clear हुआ आपको? Balanced force, have you understood? Achha, now tell me, this is balanced or unbalanced? Unbalanced. If it was balanced, then net force acting should always be 0. This is balanced force. See, net force is 0. Net force 0. Should body move or not move? That we will see. Net force equal to the, many children have a confusion. They think that if the net force is equal to 0, then body is at rest. This is a big thing wrong. Get this out of your head. Net force equal to 0 does not mean body is at rest. यही चीज हमें सीखना है. इसी से जन्म लेगा न्यूटन्स लॉज. Not at all. I'll give you example now. Net force equal to 0. ठीक है ना? Clear? Net force equal to 0 means that the body may not be in equilibrium. Equilibrium, do you understand? Equilibrium is when the position does not change, right? So there are two types of equilibrium. One is static equilibrium, one is dynamic equilibrium. Net force equal to 0 does not mean that the body will be at rest. Let's see some more examples now. Let's take an example. See a ruler sort of a thing, right? See this scenario. 4 Newton, 4 Newton. One force is acting northwards, one force is acting southwards. So in this case, we will say, are the forces balanced? Let us ask our question. Are the forces balanced? Yes or no? We say yes, the forces are balanced, right? Then our next question is, what about the net force? We say net force is 0. Why is it 0? 4 Newton, if I'm taking this as positive, plus negative of 4 Newton, because this is negative, so which is equal to 0 Newton. These are the two things. And our myth was what? Body should be at rest. ये body rest में हो ही नहीं सकता है. ये rotate कर जाएगा. This will rotate. And if you actually put a nail or a screw out here, if you put a screw out here and you fix it, you can actually rotate it. In this thing, such an arrangement is known as a pivot. This is known as a pivot. Pivot joint. Ghadi ka joint, pivot joint. And it will start rotating. That's how you are actually rotating, moving your gates. The door has got a pivot. And then you are applying force, right? And the door can move. Once this happens, we will say that here a scenario happens which is known as torque. We will, anyways, that's not in your, it's in grade 11. There comes a thing which is known as, just as terms you should know, a torque gets established. A torque is something which will be giving you a twisting or a rotating effect. A rotational effect. We call it a torque, right? And just for knowledge purpose, you should know these things. Say suppose this is the line of action of this force, and this is the line of action of this force. ठीक है बच्चा? And suppose this distance and this distance are same. Say suppose these two distances are same. Let's say this distance is A, this distance is also A. So what we have done, we have taken a pivot point. From the pivot point, we are giving a force of 4 Newton on this side, 4 Newton on this side. So what do we have? We have two equal and opposite forces, right? Two equal and opposite forces separated from the pivot by a equal finite distance. Finite means fixed, okay? Finite distance. And this finite distance was A, two equal and opposite forces. Let's say this is F, where our F is 4 Newton. This thing gives birth to something which is known as a couple. And you see this every day. Car steering. A couple makes everything more interesting and more easy to work. Then if you see municipality, those the manholes, have you seen them opening with a T-spanner? Have you seen a T-spanner? There are some bolts which are right below, like the car battery bolt. I want to replace my battery. The bolt is right below. A straight spanner, horizontal spanner will not go in. So what do I create? I create a T-spanner. You want a T-spanner? I have it here. So the T-spanner will have a hexagonal hole out here. You will put it on the bolt and you can just, so what do you do it? You are having a couple. Tap. How do you open a tap? Couple. You're pushing with the same force this side and this finger pushes on the traditional tap, not the Jaguars or the Kohler, you know, the gaon wala jo. Adya is so close to the camera screen. She's almost like what do you call those ISS mission cosmonauts return, na? Their faces come with, the only thing is missing, her helmet is missing out there. If it was an iPhone or something, it will say you are too close to the screen, right? She's too close. Please move back, right? You're with a laptop or tablet, Bittu? Which one are you?
So right now tablet.
Tablet. That's why the clarity is so much. Laptop cameras are not that clear. So this is called a couple. Not in your syllabus. What is a couple? A couple is an arrangement of equal and opposite forces separated by a finite distance, and these applications of couples are seen in T-wrenches, T-spanners, steerings. The steering is designed in such a manner. You see, when many people, when they learn driving, the first wrong thing they will do is that they rotate steering like this. Ladies have a common habit. If you make any girl or a lady learn driving, she will always rotate steering. No, the steering is not supposed to be rotated like that. The steering is to be held in 10-10 position, 10-10. And the way you rotate is that this hand will come right to your belly and this hand comes this side. It is designed. And this hand can come here and this side. And that's why I always say, when you drive, you should drive it like my car, my car, my car. Turn it. You don't turn like this. Girls have this common habit. I mean, I've seen this with my daughter. Whenever confusion comes, they will rotate steering. Steerings are designed to be rotated in this manner. Bring it till here. Again, bring your hand here. That's a couple. Okay? So, ये भी हो गया. Clear? So, I think the question arises, again, same thing. Sir, do balance forces not create a sense of equilibrium, or the body will be at rest? Yes, it will be at rest if the balance forces, which is actually formed by two equal and opposite forces, share the same line of action. See, this is my trackpad. I'm pushing it from this side, this side. This is the line of action. Now it will be in rest. But if I do this, it rotates. Right? So the only scenario where you can expect that in balance forces also, I am going to have what? I am going to have equilibrium is something like this. And this is known as the body is in static equilibrium. Now this body will be at rest. Say this is 4 Newton and this is 4 Newton. Now this body will be at rest. But if you make little bit difference in these two forces, line of action, the body will not be at rest. The body will immediately experience a couple. And once a couple comes to play, it will rotate. Okay? Clear? Chaliye. बहुत अच्छी बात है. Very nice. Very sharp children. This is an equilibrium. A static body is at static equilibrium. Or the body is at rest. You can just write body is at rest. Which one? Couple. Couple is the arrangement where two equal and opposite forces, equal and opposite. देखो इसको हम couple नहीं बोलेंगे. Here also it is equal and opposite, but they are not separated by a distance. They should be separated by a distance. Just see this diagram. Okay, let's see this diagram once again. Let me create the pivot point out here. This is the pivot point. Try to see. Now here, if this is the pivot, this force is also coming and hitting this point. This force is also coming and hitting. This is not couple. Couple ke liye, this force should be a little bit up. This should be a little bit down, but equally up and equally down. That's why the engine steering is made in that manner, so that your both hands come and fit. So this is A. This is A. Two equal and opposite forces separated by a finite distance from the pivot point will constitute a couple. And whenever couples come, this is a couple. What is the net force? 0. What is the forces balanced? Yes. But is the body in rest? No. Couples will never make the body, वो घुमा देगा body को. But यहाँ पे नहीं है. This is not a couple. Tab घुमाते हैं ना हम, वहाँ भी couple लगता है. Anything जहाँ दो हाथों से आप काम करते हो. You can go, if you have a younger brother, pull 1 ear and pull 1 ear on the same couple. Oh, that's washing machine. 1, 2, 1, 2. My Maharaja mixer gives me the super convenience of 3 separate jars. Okay, understood? Who had that? Those are our childhood days, na? I had that. You can go to YouTube and say Maharaja Mixie 1, 2, 3, Maharaja Mixie. I used to do this in schools and get first prize. So these are in my. No in between washing, no waste of time. Chalo, aage. Ye ho gaya. Brings us now to understand the Newton's laws. Now some stories. Newton's laws of motion. There are 3 laws of motion which are attributed to Sir Isaac Newton, but there is a lot of do numbers in these laws also. Okay. The first law is known as Newton's first law, Newton's second law, Newton's third law. Newton published a book in Latin whose name was Principia. In that book, these laws are there. But the Newton's first law of motion, which Newton had written long before that, means when Newton was born, even before that this person died, his name was Galileo. Galileo Galilei. He was an Italian astronomer. Okay. Galileo's law of inertia is exactly the same as Newton's first law of motion. So if you read the two books, you will find that this has been documented long back. However, they just speak the same thing. उस जमाने में तो उतना copyright था नहीं ना. So and they were like, one is a Brit, one is an Italian guy. But Galileo's law of inertia, I mean, it's almost 80-90 years apart. But however, you will keep on listening Newton's laws of motion, Newton's laws of motion. Newton's first law of motion is Galileo's law of inertia. The first law of motion is very easy for us to understand only for the first part. Today we won't be able to, I think, complete. I want to take very good time to make you understand these laws. So in order to understand these laws, let us actually see what is Galileo's law of inertia and what is that experiment all about. Okay. So this is actually performed in labs also. Right? So this is, first try to understand. Suppose a ball has been taken on an inclined surface. This inclined surface is something like, it's not this much, it's more V, so that the ball can actually come to the V. Right? So if this ball is allowed to roll, what do you observe? What should happen? What should happen? No, the ball will not stop. I have made it pointed, the ball will climb up. So the observation that was made was that this ball will exactly come up to the same height. This you can do in labs. First diagram I'll draw properly so that you get a fair bit of understanding. If the height is, say, h on this side, and the ball is allowed to roll, roll means it is falling under gravity. The ball will climb up and go here. Understood? Now what Galileo did in the experiment, Galileo's experiments were, Galileo in the second term, what he did, he actually increased, this was a steeper angle, he reduced the angle, right? But to his observation, he found this was one, say this was attempt, say this was attempt 1, this is 1 dash. When the attempt was 2, the ball exactly came here, 2 dash, same height. Okay. After that, so you must have understood now, there was third time is further increased. It still comes to the same height. It still comes. So let us say there was the third attempt made here. The ball came here. This is 3 dash. Question arises, which is a very nice question. Sir, if we actually keep the inclined plane only this much, now the plane's height is less. Here, this is our observation number 4. Here a very nice observation will be there. The ball will come till here, no doubt, and the ball will fly out till this position and then fall. Right? So once all this thing is done, that's what we don't think like scientists, is that what about if I would have made it parallel? This is, if you understand this, you understand Newton's law. What am I observing? That no matter what is the inclination, the ball always reaches to its particular height. The ball wants to gain that height. Please understand what I'm saying. The ball is very stubborn. It wants to gain that height. You did a lot of atrocities with it. It changed the inclination, yet you could not stop it from gaining its height. The ball is ready to travel additional distance, but मैं height तक जाऊंगा ही जाऊंगा. And here you reduce that distance, still the ball climbed up to that height and then it fell. Now once you make it parallel, is it parallel? Somewhat parallel. I told you one thing. What is the ball adamant about? Reaching the height. What does he do here? How will he jump up? There is no jumping up. That's what I'm saying. It can only have a rolling motion. The lab design is such that it can only have rolling motion. Jump कैसे करेगा? यहाँ से see, this is our attempt number 5. This is our attempt number 5. Children, this is 5. And if you have slight bit of confusion, then this was your first slide, second slide, third slide, fourth slide. This is your fifth slide. When your fifth slide is designed, 1, 2, 3, 4 is not present. I can't draw so many diagrams. So it is only this and this. The ball will not bounce. The ball can only roll. What is the ball adamant about? Gaining the height. So what will it do? What will it do? The ball doesn't mind to. The ball doesn't mind to travel any distance. Any distance. The ball will keep rolling till eternity. But in reality, this does not happen because you have got air friction and you have got surface friction. If those two things are removed and we get into an Alice in Wonderland sort of place, which is called the Newtonian environment. A Newtonian environment is an environment where no forces of obstruction, repulsion, all these forces do not exist. Only it's a lab, it's your proper lab. If it was a Newtonian environment, then what do you expect this ball to? The ball will be relentlessly fighting to gain its height. And for that, it will do anything in this world. So it will keep on rolling till eternity. That is Galileo's law of inertia. We will continue in next class also, but listen what I am going to say now. Galileo's law of inertia and Newton's first law has got two parts attached to it. The first part is very easy for us to believe because things happen that way as we see it in our daily world. The first part is very simple. It says a body at rest remains at rest. What is so difficult to, I've deliberately written it in uppercase. A body at rest remains at rest. My trackpad is at rest, my cell phone is at rest, they remain at rest. A body at rest remains at rest. Does your heart agree to it? Yes. You see things like that. You don't expect the cow to fly away unless you push the cow, right? But the next part is something that our heart does not agree to it. The next part says, and a body in motion, every word has importance here, continues to be in uniform motion. A body in motion continues to be in uniform motion. My mother should be very worried that I left her house and came here. I should be walking in uniform motion throughout. I should not stop. That is what her heart does not believe, right? So the second part is something which doesn't happen every day. A body in motion will remain in its state of uniform motion. We say a body in motion continues to be in its state of uniform motion. Now both the laws have got a criteria. Unless it is, listen, acted upon by an external force, I will keep a word here called net force. Net force. And I'll come to that word to change. Unless it is acted upon by an external force that compels it to change its state, its state of rest or of uniform motion. Now let's read the law once again for the first part only, just for the first part. A body at rest remains at rest unless it is acted upon by an external force that compels to change a state of rest. I am at rest, I remain at rest till some mule kicks me, external force, to change my state from rest to motion. Heart agrees to it. A ball on the billiard board remains at rest until an external force compels it to change its state. A body in motion continues to be in a state of uniform motion. So when I say uniform motion, at least now you understand something, that during this phase, acceleration should be zero. Then only it's uniform motion. Uniform motion, a body is said to be in uniform motion if it covers equal displacement in equal intervals of time, no matter how small the time intervals are. So a body will be in uniform motion. A body in motion continues to be in a state of uniform motion, continues, unless it is acted upon, and that part is what happens in daily, unless it is acted upon by an external force, air friction, surface friction, or say gravity alignment, whatever it is. Gravity of the earth is also pulling the ball now, so the ball is slowing down to change its state of uniform motion. If you delete air friction or air resistance, if you delete what you call rolling friction, if you delete the gravitational pull of the earth, then there is no external force acting on it. There's no net force acting on it. The body will continue in uniform motion. This will be in uniform velocity. Till when? Till you don't introduce that intruder. Who is the intruder? Net force. Net force. Net force. And when the intruder is introduced, that is the net force is introduced, the body will lose its state of uniform motion. It will come to stop. So what it has to do? It has to retard. Acceleration will come into play. So from here we understood one thing today. We understood one thing. This is our years. Remember this thing in physics. The moment you hear that there is any system where there is a net force, you should immediately say acceleration is born. This acceleration can be positive, can be negative. In all these cases of a billiard ball or a pool ball being hit, the ball stops because the ball retards. Why? There is a friction. There is air resistance, there is a gravitational pull. They are all going to act as what? The net force. And how is the net force? The net force is acting opposite to the direction of motion. So definitely it will create retardation. So one thing we have understood, if there is net force, there is acceleration. Go back to chapter 1. Your chapter was all about uniformly accelerated motion in a straight line. So you prepared all those dishes in which one of the ingredient was A. So in all those questions, net force is applicable. वरना A का जन्म ही नहीं हो सकता है. So what type of numericals we can expect now? We will expect numericals where force will be there, A will be there, and the same scenario of pull down. Rather than calculating only the facets of motion, they may ask us to calculate force also. So Newton's first law or Galileo's law of inertia, we have just understood maybe 20% of it, just 20%, not more than that. I'm glad you understood this experiment. It just tells me the qualitative part of force. By this law, in no way I'm able to measure force. हमें तो measure भी करना पड़ेगा ना. That measurement will be given by second law. And the third law is very stylish. In what that's English literature. That is not third law. The third law for the first time says that you always have a body on which force is acting, force is acting, force is acting. Is the body your slave? Can the body not retaliate? The first time the body is given the authority to also exert force. If you apply force on the body will also exert force. That authority comes from the third law. So Newton's third law analyzes how a body can also exert force. Your body is not your slave that you'll only apply. Then let us take a body and apply a force. That the body should also exert a force to you. So the first law tells me that as long as a body does not have any external force, I'll take 5 minutes more. One nice example, otherwise you'll lose it. External force, the body is said to be in uniform motion. So in order to cancel acceleration, you have to first ensure that no net force acts on the body. let us see one example and see whether we have understood that or not. One of my very interesting examples. This is the ORR, straight. Okay, and on this ORR, this is my sedan car which is moving, right? And we are moving with cruise control. Cruise. That means we are moving at 50 km/h fixed, and we are going east. So is the V constant or not? Tell me. The V is constant. Agreed? Is the acceleration in this case 0? Yes. That's why you're not pressing the pedal. You have just put it on cruise. And those who do not have a cruise car, you can't release nor you can press further. एक point पे पाँव रहेगा दबा हुआ. जब भी छोड़ दे वो नहीं, एक ही जगह पे कांटा एकदम 50 में. That means all that we have studied, Fnet should be 0 out here, right? Good. So let's see. I hope you have been able to think what I'm saying. Vehicle is moving in this direction. Huh? Here, this is the weight or the pull by earth. Yeah, these are friction. So many forces are acting against you. Right? These are all our forces. So let's say we have our friction due to air plus we have friction due to wheels. All the directions are different. I'm just saying, and say the gravitational pull of the earth. All these I am replacing with one force called F enemy. This is my enemy force, F enemy, right? My diagram would become something like this now. Okay, give me 1 minute more. My diagram is something like this. Can I not bring one F enemy? I'm trying to just simplify them. What is motion? Car is still going at a speed of how much? 50 km/h. And you are trying to say A equal to 0, V is equal to constant. Constant is represented by K, right? And F net is equal to 0. Kahan F net 0 hai? How is the body then? Kahan F net 0 hai? But Newton's laws, Newton's laws are never proved. There is no proof of Newton's laws. But there has nothing been found in the universe that does not obey Newton's laws. Newton का law कभी proof नहीं होता है. कहाँ है यहाँ पे F net 0? F net 0 आप बोल रहे हो ना? No, but F net has to be 0. Give me the explanation how the F net is 0. Because if the F net is not 0, you will not be able to, the vehicle should retard. There is a Dushman force which is acting against you. Array, you dumbos. Why did your parents spend that 15 to 16 lakhs on the engine of the car? The engine of the car is giving a force which is the F engine exactly matching with the F enemy. Then only it will be. Now put Newton's laws. A body in motion continues to be in a state of uniform motion unless and until it is compelled by an external force. Right now, the engine will give a force. The tractive force is exactly equal to the enemy force. Body is going at uniform motion, right? So no net force. Now we'll create net force. How to create net force? Now suddenly what happens? There is someone, let's say Ryan suddenly appeared on the road. So we have to brake this car. If you brake the car, the engine force reduces. Dushman force remains the same. Has an imbalance been created? So F net is applicable now. The F net is now acting on this direction. Its state of uniform motion is broken. We are not worried about it slows down or it speeds up. Its state of uniform motion is broken. Another scenario. let's say from here we suddenly encounter a slope. The gravity will be now in my favor. So the total force F engine means the tractive force increases. An imbalance is created. Acceleration will be seen positive. Body will pick up. So let's go to Newton's laws. A body at rest remains at rest. Very easy to understand. A body in motion continues to be in a state of uniform motion unless and until it is acted upon by an external force to change a state of rest or of uniform motion. पहले याद मत कीजिए, पहले समझिए, सालों साल याद रहेगा. Till you do not bring a net force. Again, I'm saying this is the most important diagram of our discussion today. Here about net force, acceleration is born. That means uniform motion ceases. You know the meaning of the word ceases? Uniform motion ceases. Understood? Uniform motion ceases. And once uniform motion ceases, velocity will change. That means an initial velocity and a final velocity will be created. Let's go back to our example. If we brake, then our initial velocity will be more because we brake from 60, final velocity is 0. So retardation will be born. And if we are getting a slope, initial velocity was 60, final velocity will be 80, acceleration will be born. ठीक है? समझ में आया?